All right. Good morning, everybody, or good afternoon. Obviously, you can tell I am not there with you today, but hopefully this little tutorial will be beneficial and can aid in your understanding of Lewis structures, something that you might be familiar with, or you may not remember anything. That is okay. Again, today's class as well as next class, which I will be there for, we'll be going over Lewis structures. So Lewis structures are a more condensed version of your Bohr diagrams. Last year, you may have been introduced to them, specifically drawing just the Lewis structures of individual atoms. In grade 10, we are going to be going further and starting to draw the diagrams for ionic as well as covalent compounds. But I wanted to do this brief review. It's not going to be comprehensive. You have a worksheet that should be handed out to you soon, if not already, that goes into depth about valence electrons as well as the octet rule and all these different terms and how to draw them that I want you to practice. But hopefully this little tutorial will get you into it. You can practice and then we can move on to talking about ionic compounds later in this tutorial. And there's also a worksheet that should be handed out to you regarding that. Okay, so let us start off by just kind of reviewing some ideas or knowledge that you may have learned about, you may not have. So first of all, I want to introduce to you our handy dandy periodic table. Now this periodic table is going to be the exact one that you will have on every assessment we do in class, as well as for the final exam in chemistry, or I should say science 10. So I would highly recommend getting used to using this specific periodic table and identifying where the information is. It's going to help you a lot when it comes down to the assessments. All right. You should also have, there should be a green folder in the classroom where you can take one of these periodic tables. Please just make sure at the end of class to put it back in the green folder. All right. So looking at a periodic table, let us start off with something easy like lithium. So if we take a look at our legend here, that's included, we can tell that our number 3 up here refers to the atomic number. And the atomic number is really useful because it tells us 2 pieces of important information. Number 1, the number of protons. Protons, obviously, are those positive particles that exist within the nucleus of an atom. And then we also have something that even a little bit more important, at least for us with drawing Lewis structures, is our number of electrons. So in this case, we can see with lithium, we have 3 electrons. Now, when you would be drawing your Bohr diagram, this won't be a perfect Bohr diagram. Usually within the nucleus, you include the number of neutrons and protons, but we're not going to do that just because we're not super focused on a Bohr diagram today, but we'll use it as an example. So in our first shell, we know that there can only be 2 electrons. That's the maximum that shell, that energy shell, can hold. But we have 3, so we need to add 1 more shell and our 1 more electron. And this shell is really important because it is called our valence. Valence shell. Valence shell just is talking about how this is the outermost shell of the atom, all right? And similarly, this electron, because it exists on the valence shell, would be called our valence electron. Okay, so why we care so much about our valence electrons and our valence shell is because when it comes to bonding, which we're going to be interested in this quarter, the valence shell is what does all the bonding. The valence electrons participate in the bonding. The innermost, so these guys here, let's see, do I have a highlighter? Yes, I do. These guys here don't participate in the bonding, so we're not really interested in them right now. What we are interested in is our valence electrons. Okay, so If we want to draw the Lewis structure, all we need is to include the atomic symbol. So in this case, it's a capital L with a little I, and then the valence electron. And we only have one. So that's our Lewis structure. Okay, let's do one more example as a bit of a refresher. Let's do something with more valence electrons, like nitrogen. So nitrogen has 7 electrons. We'll do our Bohr diagram just again to show the whole structure. So we have 1, 2, and then we need to make our second shell, which can hold 8, right? So 1, 2, 3, 4, 5, 6, 7. All right. So that's our Bohr diagram. And I want to emphasize the fact that while I was filling up that second shell with our electrons, I went in a clockwise manner, adding one electron at a time until I started pairing them up. And I want to emphasize this is really important for Lewis structures as well, and can cause, if you don't pair them up properly, you don't follow this rule, it can lead to errors or mispairing and create confusion later on. So I want to emphasize it's really important, as much as it sounds or feels kind of redundant or unnecessary, it's really important that you follow this rule and just add one electron at a time and then start to pair them up. So if we were to draw our Lewis structure for nitrogen, again, we're following this rule of adding one electron at a time and then pairing them up. So we see that there are one group of paired electrons, and then we have 3 lone electrons. So electrons like to be paired, we know this, but these guys are alone. They're on their own and they won't pair up together. Okay, and this is what leads to bonding. These 3 unpaired electrons are going to be looking for other molecules to bond with that also have these lone electrons. And through that, they're either going to give or take in an ionic compound, or they're going to share like in a covalent compound. So we're going to get to that in a second, but I want to emphasize this is how you draw your Lewis structures for a regular atom. If you don't want to draw Bohr diagrams all the time, which I encourage you not to, because they take a long time and they're not really important, there's a quicker way to identify how many valence electrons a certain element will have, and it's by the group numbers. So you can see at the top of each group of the periodic table here, we have a bunch of numbers, right? So in our alkali metals here, they're all under group number 1, and that's because, well, one of the reasons at least, they all will have 1 valence electron. So no matter which of those you get, for example, sodium, your Lewis structure, you don't have to worry, you know it's only going to have 1 valence electron. So there you go. Valence Lewis structure of sodium done. Same with cesium. Even though it has 55 electrons, it will only have 1 valence electron. So that's what its Lewis structure will look like. Okay, next one over, next group. So group number 2, all of those will also have, all those different atoms or elements will also have 2 valence electrons. So calcium, 1, 2. Same with barium, right? 1, 2. Even though it has 56 electrons, it will always have, its Lewis structure will always be 2 valence electrons. Now, something kind of tricky goes on with our transition metals, which are these guys here. All right. And so we're not going to be focusing on them this year, and you don't have to worry about them. They get a little funky. However, on our nonmetal side, we can see that we also, again, have our group numbers, but now they're in the 13/14 range. We can still figure out how many valence electrons from this. They don't have 13, they don't have 14. What you have to do is take the group number. For example, if we're looking at boron, you take the group number, which is 13, and you minus 10. So that means it's going to have 3 valence electrons. Aluminum is going to have 3 valence electrons. Gallium, 3 valence electrons. They are all the ones in the group are going to have 3. Same thing if we go to oxygen, right? Oxygen's group number is 16. We are going to subtract 10, and we are going to be left with 6. So oxygen will have 6 valence electrons. Sulfur, selenium, tellurium, all will have 6 valence electrons. So I want you to go ahead now and work through the problems, and then we'll come back and I'll give a brief tutorial on ionic compounds. Good luck. All right, welcome back. Hopefully you found drawing Lewis structures of regular atoms not too bad and are ready for another challenge. So I'm going to be introducing ionic compounds and how we are going to be drawing those, the Lewis structures. So ionic compounds, hopefully you remember, are between a metal and a nonmetal. So if we look at our periodic table, a metal is going to be anything here. So anything in the blue, yellow, or green. So we know from our procedure the other day, our calcium lab, calcium's a metal. We have our iron, cobalt, aluminum, like aluminum foil. These are all metals. And I want to also point out the fact that if you look at their ion charges, which will soon become very important and we'll be working with a lot this quarter, they all have positive charges, right? No matter where we go in the metals, they all have positive charges. And our nonmetals are anything kind of not included in the metal. So that means our hydrogens, and yes, hydrogens found on both sides, our hydrogens, and anything in the kind of orange and blue here. Those are all considered our nonmetals. However, we're not going to be really focusing on our noble gases because they don't bond very often. But you can see all the rest of our nonmetals all have negative charges, except for hydrogen. Hydrogen, we are going to be dealing with hydrogen. Anytime you see hydrogen, it's going to have a positive charge. So it's kind of an exception to this. All right. So ionic compounds, we always have a metal and a nonmetal, and it's important to note that the metal always goes first when we're writing an equation, right? For example, if we have sodium chloride is just table salt. Something you consume every single day and is actually quite important for our body to function properly. So table salt, we have our sodium, right? Which on its own is quite of a reactive alkali metal, right? If you put it in water, it'll start to explode. And then we also have our chlorine, which is in its natural form a gas. Okay, and is also very toxic, but when you put them together and they bond, they form something that we consume every single day, table salt. It's kind of, I find that really cool. Two very on their own dangerous and toxic materials, but when they bond together, they form a whole new compound that is vital for our everyday function. Anyways, so when we want to draw ionic compound, we have to recognize that in order to form these compounds, an ionic compound, they are going to trade electrons. So sodium is going to give up some electrons to chlorine, and let's take a look at their Lewis structures first to kind of understand the transfer electrons. So let's draw sodiums. Sodium has, if we take a look, it's in group number 1, so that means it's going to have 1 valence electron. And our chlorine right, is in group, let's see, group 17. If we take 17 and we subtract 10, that means we are going to have seven valence electrons. So let's add those in. 4, 5, 6, 7. Okay. So if we take a look at our valence electrons, we can see that chlorine has 1, 2, 3, 3 groups or 3 pairs of electrons. So those pairs are happy. They want to stay paired. We only have one singular electron that is unpaired. That means it's unhappy. It wants to find a buddy. And on sodium, we have one singular valence electron. It doesn't want to exist by itself. So I'm going to ask you this question. Is it going to be easier for chlorine to strip away that one valence electron from sodium and take it for itself, right? Or is it going to be easier for sodium to take away all the extra valence electrons, all 7 of them, from the chlorine to make itself happy? What do you think? To just donate or give up its 1 electron to chlorine, right? I also want to remind you that sodium, because we are dealing with Lewis structures, but if we wanted to draw out the whole Bohr diagram, right? Sodium has what, 11? So it still has 1, 2 full shells underneath, right? It only has that 1. So it's actually beneficial for sodium to give up its 1 valence electron too, because then it's left, if you get rid of its 1 valence electron, then it's left with a full shell and it satisfies the octet rule. So not only is chlorine happy by getting that 1 electron, right? Not only is chlorine happy because now it satisfies the full octet rule, but sodium is also. It's gotten rid of that 1 electron that was kind of messing it up. So this transfer is beneficial for both sides. And when we draw our Lewis structure to represent this change, what we have to remember and what we have to show is the transfer of that electron from sodium to chlorine. And how we do that is we use these square brackets. So sodium has lost its electron, right? It's transferred it over to chlorine, and we're going to draw a square bracket around sodium to represent it's an ion now, which means an atom who has lost or gained an electron, right? It's lost an electron, so it's going to have a positive 1 charge. This is because, right, an atom is neutral, meaning it has the same number of protons as electrons. That's what we get from our atomic number, remember, right? But we've given away 1 of the electrons. So if we have 11, right, our atomic number for sodium is 11. If we have 11 protons and we had 11 electrons, and we gave away 1 of our electrons, now we have 10. So if we look at this ratio, we're leaning more positive now. We have more positive charges, even though it's only 1 more positive charge than we have negative, but it's now unbalanced. It's not neutral. So we draw this little symbol up at the top and give it a positive 1 charge. We have to do the same thing for our chlorine, but this time we have to include all the little electrons. It has a full octet now. And how many electrons did chlorine gain? It gained 1 electron. So we're going to have a negative 1 charge. Okay? These charges are just also found on your periodic table, right? If we take a look at sodium, it has a positive 1 charge, and our chlorine also has a negative 1 charge. So if you're ever in doubt, just look at the charges when you're drawing these Lewis structures of ionic compounds. Just look at the charge on your periodic table that's listed, and that's going to be charge you use. But you should understand why we or how we get these charges. It's because we are changing the amount of electrons we have. Either we're gaining some or we're taking some away, and that balance is no longer there. That neutrality is no longer there in the atom. It's now an ion. So it either has one more electron or it has one less. So that would be our ionic Lewis structure for sodium chloride. Let's do another example. Beryllium nitride. Okay, so beryllium, if we draw its Lewis structure, beryllium, let's take a look. It is all the way here in group 2. So we know it has 2 valence electrons. And nitrogen it's in group 15, so it has 5. 1, 2, 3, 4, 5. Okay, so last time we could easily see that it would transfer its 1 electron. This case, would beryllium be more likely to take the 5 electrons to give itself a full octet, or give them away? It would more likely give them away, right? So 1 electron would float down there, pair with that electron, that lone electron, and 1 would pair with this one. However, that leaves us with a lone electron still. That's not good. That doesn't satisfy our octet rule. So what do we need to do? Well, let's add another beryllium atom. Okay, we know beryllium has 2. All right, we now have another electron that can pair. Okay, with this one. So now our nitrogen is happy. It has a full octet, but now we have the opposite problem. We have a lone electron on beryllium that has nowhere to go. So let's add a nitrogen. Okay, this beryllium. Okay, its lone electron can go there, and then we still have 2 lone. So let's add 1 more beryllium. All right, can give away its electrons to nitrogen, and now we should be happy. Now it should be content. All electrons, all the beryllium electrons have been given away. All right, so we have 3 beryllium atoms, and all their electrons have been given away to the 2 nitrogen. So in total, we have moved or given away, right, 6 electrons to the 2 nitrogens, right? We can see we have on each nitrogen, there's 3 unpaired electrons. So that makes sense mathematically. So if we were to draw the Lewis structure, okay, we can draw, first of all, let us write beryllium, right? Remember the brackets because it's an ion. Beryllium, each beryllium gives away 2 electrons, right? And beryllium has 4 electrons and protons. So if we have 4 and then we give away 2 of our electrons, we are going to be +2. We are going to have 2 more protons than we do electrons. So we're going to have a +2 charge. And then I also want to say, because we have 3 beryllium atoms, we are going to represent that by putting a little subscript of a 3 at the bottom. That basically means if we were to expand this out, same math rules, right? That would mean we have beryllium 1, okay, beryllium 2. Each beryllium has a +2 charge because each of them gives away 2 electrons. Beryllium 3. Okay, that's what this means. So now what we're going to do is we need to take care of the nitrogens. So let's see here. All right, we'll clean up, take away these guys at the bottom to make it a little bit cleaner. All right, so nitrogen. Remember, we need to include all of the little electrons to show it has a full octet. All right, And each nitrogen gets 3 electrons, extra electrons from our beryllium. And because we have 2 nitrogens, we're going to add a 2 subscript at the bottom. Again, if we were to expand this out, mathematically, we could see this right here, right? We would have 2 nitrogens, each gaining 3 electrons each for a total of 6, and 3 berylliums giving away 2 electrons each for a total of 6. Okay, so I want you to go ahead and work through the worksheet. There is an answer key for you to check your work. And next class, we will come back and we'll do a little bit of a review and then talk about covalent compounds. All right, thank you, everybody.